Assalamualaikum warahmatullahi wabarakatuh and hi, I am Syafawani Binti Fizal, a final year student of Bachelor in Science Hans Biology ITM Perlis. Today, I will present to you my final year project entitled Mechanical Properties and Degradability of PLA-PP Reinforced Durian Skin Fibers Treated with Glutamate Salt.
Nowadays, natural fibers is an interesting option as reinforcement in the productions of bioplastic. Researchers found many advantages in natural fibers such as it reinforced composite lower the density of the product. Natural fibers has acceptable specific strength, renewability, combustibility, lower durability, and it also has the excellent mechanical properties, and most importantly, natural fibers are lower in price compared to synthetic fibers. So one of the newly discovered natural fibers is durian skin fibers, DSF. DSF has the potential as reinforcing filler for the production of polymer material to form biocomposites. So glutamate salt, or GP, is the new discovered treatment used to enhance the addition in biocomposite productions. According to Pang et al. 2019, other treatments are like alkaline treatment, acetylation, and the use of coupling agents such as saline coupling agent. Samsudin et al. 2016a reported that GP is produced by reacting palmitic acid and L-glutamine. The past studies lack of discussion on the effect of mechanical properties and degradation's activity on hybrid biocomposite. There are not much research have been done on GP ability as a compatibilizer to bioplastic. Hence, in this study, a hybrid biocomposite of PLA-PP reinforced with DSF and addition of GP as compatibilizer is observed. Jiang et al. 2022 reported that synthetic plastic is difficult to break down. It results in long-term waste of land resources in landfills. Malaysia grows many kinds of fruits like durian and therefore produces abundant amount of durian peels each year. According to Charo Envi 2014, this agricultural waste is expected to increase in the future if poor waste management is implemented. Social and environmental issues may also arise from this. This study is significant as it is in line with the Malaysia 12 plan for 2021 to 2025, which is Advancing Green Growth for Sustainability and Resilience, which was proposed by the government. And this project will also help government to objectify Strategy A3, which is the sharing responsibility and pollution prevention in the plan by helping preventing the amount of agricultural wastes. This project is also in line with the 17 Sustainable Development Goals (SDGs), which proposed by United Nations member states. And this project also can contribute to Goal 12, which is to ensure the sustainable consumption and production pattern in which promoting minimization, reuse and recycling of solid wastes by converting wastes into goods. In total, there are three objectives of this study. So the first one is to determine on the potential of durian skin fibers as natural filler treated with GP in hybrid biocomposite of PLA-PP. Next is to investigate the effect of GP on mechanical and physical properties of PLA-PP reinforced DSF hybrid biocomposite. And lastly, to determine the biodegradability of hybrid biocomposite of PLA-PP reinforced DSF treated with GP using soil burial tests. So, according to Timbangan Sembering et al. 2018, tensile strength of the SF composite reinforced by polyester resin rose as the composition of the composite increased. However, as the fiber composition keep on increasing more than the polymer material composition, the mechanical properties will decrease. In the same study by Timbangan Sembering reported that the impact strength is similar to other mechanical properties, that is, it increases as the DSF composition increases. According to Anwar et al. 2018, PLA reinforced with DSF has the greatest weight loss due to the high compatibility of natural fibers in the environment, which have caused the sample to decay more quickly in soil. Previously, study on PLA properties incorporated with other natural fillers have also been made by previous researchers. So according to Russell et al. 2010, PLA has similar tensile strength and elastic modulus to polyethylene terephthalate PET, a biopolymer, but it is also exceeding brittle with less than 10% elongation rate, and low toughness, limiting its use in applications that need plastic deformation under high stress. Yusuf et al. 2021 reported that PLA incorporated with tapioca starch shows an excellent mechanical properties of the composite produced. The greatest tensile strength achieved is higher than the plain PLA. There are also some studies on the effect of GP as compatibilizer in biocomposite made by previous studies. A study by Samsudin et al. 2016a reported that inclusion of GP in the formulation increased the tensile strength of the HDPE reinforced with silica composite when compared to control composite without GP. Another study by Muhammad Zaini et al. 2019 reported that tensile modulus at elongation 100% of both composite system of EDPM reinforced purolite, having greater modulus than EPDM with the addition of GP reinforced with the purolite composite. This is due to the presence of GP is an internal plasticizing agent, which altered the composite flexibility and hence reduced the stiffness. According to Samsudin et al. 2016b, in the study, the impact strength rose as the more surface areas are coated in GP. Now I will explain about the methodology used in this study. So the fruit waste used in this study is Dureozubitinus murray, or the durian skin fibers. We use it as the natural filler, and polylactic acid PLA and also polypropylene PP were used as the polymer metric, and good palmitate salt or GP is used as the compatibilizer. The GP was synthesized via titration process in the laboratory. Composition of the SF were varied from 0, 15, 30, 45 and 60 php, while the PLA and PP were fixed at 75 and 25 php respectively. So 3 php of GP was mixed in the hybrid biocomposite. Sample 1, which is the control sample, only consists of PLA PP polymer metric, while sample 2 until sample 5 is consists of the PLA PP with the addition of durian skin fibers at different filler loading and also addition of GP. And this sample, we call it as the treated sample. While sample 6 consists of the PLA PP with the addition of DSF but without the GP, or we call this as the untreated sample. For the preparation of hybrid biocomposite, all the hybrid biocomposite components were mixed in the melt mixer machine using the melt blending method. The addition of components is based on their melting point. First, PP was added into the mixing chamber, then followed by PLA, DSF, and finally GP. After all components in hybrid biocomposite is fully homogeneous, then we need to produce a slab. So in order to produce a slab, we need to use compression machine. It takes for about 25 minutes for the hybrid biocomposite to be fully mixed and melted. And yes, it looks like we are baking a cake. And surprisingly, the mixture smells good too. So this is how the slab of hybrid biocomposite looks like. This slab was then cut into small specimens according to ASTM standard for testing. There are 5 testing have been conducted on the samples in this study to observe the result. The testing are listed as follows. According to Samsudin et al. 2016, a broadband OH extending from 3500 to 300 cm, indicating the presence of GP. So, in this IR spectra of treated hybrid biocomposite, it can be seen that there are a broadband of OH, indicating the presence of GP in the hybrid biocomposite. From the table and also the graph, it can be seen that the increase of the SF filler loading treated with GP lead to gradual increase of tensile strength of biocomposite. By looking at the figure, it can be seen that sample 5 treated with GP exhibit the highest tensile strength with the value of 5.14 MPa. This is due to the addition of GP as compatibilizer in all biocomposite except sample 1, which is the control sample, and sample 6, the untreated sample. According to Samsudin et al. 2016a, compatibilizer act as an additive used in most reinforced filler composite, primarily to increase compatibility at composite interfaces, which are often incompatible due to the non-polarity of the polarimetric and polar character of the filler. DSF has a hydrophilic properties, while PLAPP has the hydrophobic properties. Hence, the addition of GP will glue both filler and polymer matrix together. Anwar et al. 2016 also reported that the compatibilizer also plays a positive role in enhancing the tensile capabilities of filler and polymer matrix composites that leads in increasing tensile strength. The findings show the tensile modulus decreases when the SF loading rises. The increase in the SF filler loading in the composite making it become less stiff. The composite is more flexible and less resistant to deformation as more filler is loaded in the polymer matrix. According to Subrata Chandra Das et al. 2021, rising the filler loading result in declining of modulus, most possibly due to the agglomeration of filler in the polymer matrix. On the other hand, sample 6, which contains 60 php DSF without the GP as compatibilizer in the composite, shows a tensile modulus of 1081.93 MPa higher than sample 5, which contained the same 60 php of DSF but with addition of GP. Higher flexibility of the composite with the addition of GP that enhanced the chemical bonding between both filler and polymer matrix. This is supported by Muhammad Zaini et al. 2019, stated the internal plasticizing effect of GP which altered the composite's flexibility and decreased their stiffness. It can be seen that the elongation at break of PLAPP incorporated with the SF composite shows a fluctuate pattern when there is an increase of the SF filler loading. Increasing the DSF filler loading to 30 php and 45 php in sample 3 and 4, the percentage start declining to 2.32% and 2.10% respectively. According to Rosman et al. 2000, at higher fiber loading, the denomination of fiber-matrix interaction is expected to diminish and being replaced by filler-filler interaction. Thus, elongation decline as additional fiber is added into the polymer matrix. Mansour et al. 2014 reported that utilizing fibers has the tendency to lower the elongation at break. However, sample 5 with 60 php DSF loading have the highest percentage of elongation at break, which is 3.19%. The rising of filler loading resulted in flexibility and less hardening of the composite. Muhammad Zaini et al. 2019 reported that the increase in elongation at break is due to the greater ductility of the composite caused by the uniform dispersion inside the composite with the addition of GP. Based on the figure and table shown, the impact strength improving from sample 1, 3 until 5. The impact strength were only tested on sample 1, 3, and 5. Sample 5 with 60 php DSF has the highest impact strength among all samples. The improvement of impact strength is because of the enhanced interfacial bonding between the matrix and filler due to the existence of the compatibilizer, whereas it facilitates better transfer of stress. Therefore, it can be said that the higher the filler loading incorporated with GP as compatibilizer gave higher impact strength. According to Samsudin et al. 2016b, the impact strength rose as more surface areas are coated with GP.
The density of hybrid biocomposite increases as the DSF filler loading increases. Higher density related to the higher content of PLAPP polymer matrix and DSF filler in the biocomposite. The density of the composite is relevant according to JISA 5905-2003, stated that the density of biocomposite material should be between 0.35 gram per centimeter cube to 1.3 gram per centimeter cube.
Swelling test is used to study the water absorption of the composite. The finding revealed the percentage of water absorption increased as the filler loading increases. However, as the filler continue increasing, the percentage of water absorption is decreased. The percentage is reduced. Abdul Aziz et al. 2016 reported composite have significantly increased in water absorption upon immersion in the water until it reached the saturation point. Ashari 2010 reported that saturation points refers to the composite absorb normal water and the water content in the composite remain constant. A soil burial test is performed to study the degradability of the PLAPP incorporated with the SF biocomposite. The test is performed for 30 days with the interval times of 10 days. From the figure, it was depicted that the fractions of weight loss in sample of PLAPP reinforced with 30 php, 45 php, and 60 php of the SF filler loading presented in the work was steadily increasing with increased days of soil burial. Increasing in filler loading caused increase in the percentage of weight loss of biocomposite, with the highest percentage loss of 23.09% after 30 days of soil burial for composite with 60 php of the SF filler. Turco et al. 2021 reported that by raising the amount of fibers, the composite become a suitable food substrate for microorganisms, and due to the formation of low molecular weight oligomers, the biocomposite could be likely attacked by the soil microorganism, hence able to accelerate the subsequent enzymatic biodegradation process. A novel single-factor analysis is performed to observe the effect of DSF relay loading in the biocomposite, while t-test is to observe the effect of GP in the biocomposite. According to ANOVA single-factor result of all tests as stated in the table, the p-value is more than 0.05, indicating there were no significance between means of each sample in the test of the biocomposite when DSF relay loading in PLAPP metric increases. While for t-test, only impact test shows the p-value less than 0.05, indicating there is a significant difference between means of two samples in impact strength of biocomposite when the SF relay loading in PLAPP metric is treated with GP. These are the final conclusions that can be made from this research. These are few recommendations to improve the study on PLAPP reinforced Durand skin fibers hybrid biocomposite. Instead of using GP, probably after this can use titanium coupling agents as coupling agent or compatibilizer. And next is to perform other tests such as differential scanning calorimetry and thermogravimetric analysis. And the third one is study the morphological characteristic of the PLAPP reinforced with DSF using SEM. That's all for me. Thank you for listening.